Glass is inherently brittle. It is the very symbol we use for fragility. But these days, we expect so much from this material. We want it to be perfectly transparent, scratch-resistant, thin, and even flexible. But most of all, we want it not to break. So is it possible to make unbreakable glass? Well, in this video, I will make the case that glass is one of the most important materials humans have ever made. It has transformed how we live, launched numerous scientific revolutions, and forever altered how we think about our place in the universe.
Part of this video was sponsored by Serlet.
In mid-2006, Steve Jobs had a problem. Apple was working on the first iPhone, set to be released in January 2007. But Jobs wasn't satisfied with the screen. The prototypes he was testing had plastic screens, which scratched easily. So Jobs wanted glass. But regular glass wouldn't work. It too would get scratched up, and it would also shatter. Plus, he wanted the phone to be slick, so the glass had to be really thin. So he called up the CEO of Corning, Wendell Weeks, to ask him to make the glass for Apple. And 6 months later, it was on the first iPhone. This was Gorilla Glass.
Gorilla Glass has been used in phones, computers, and wearable devices for the last 17 years. Now it's used on billions of devices, and over the years, it's become a lot more durable. So we sent Veritasium producer Peter to Corning's headquarters to see for ourselves how Gorilla Glass is made and how it works.
We'll need a volunteer.
Yes, that's neat.
All right, so this is what we call our key scratch demo. In here we have polycarbonate, which is basically a plastic, and then we have a Gorilla Glass. And what you can do is scratch this side first, the polycarbonate, see how it goes.
Yep, definitely scratches.
Yep.
Trying to scratch in our logo. It's not quite.
There you go.
Are we getting Veritasium?
Yes.
All right.
So now try the same thing on the other side. So this is Gorilla Glass.
Yeah, definitely does not scratch.
To break glass requires two things, a flaw and stress. To introduce the flaw, they sandblasted a spot in the middle of the glass to roughen up its surface. And Peter will apply the stress.
Take that tip and put it inside that circle and push down. See if you can break it apart. Not too hard, right?
No.
All right, so next we have strengthened soda lime. Strengthened as much as you can for soda lime. So
All right. Harder, for
harder,
sure.
a little bit. Next we have Gorilla Glass.
I'm kind of terrified. Oh, man. Right, I know like we don't actually want to do this, but I want to do this, so. Are you kidding me?
There's two responses. The first response is either, this is a really great demo, I completely understand what you're showing me. The second response is, I'm taking this personally. I need to try to break this glass.
Okay, it is a very good demo. I'm like genuinely really impressed at this point. I still want to break the glass. Right, last one. No, like I'm bending the stylus. Like, okay, amazing.
Glass has existed in nature for billions of years. It's formed by meteorite impacts, lightning strikes, and volcanic eruptions. But when humans came along, they found ways to use glass. Obsidian is volcanic glass. It forms when lava cools quickly. It's extremely brittle, so when you hit it with another rock, you can chip off sections of it to make a sharper and sharper edge. There's evidence of obsidian being used for cutting implements, arrowheads, and tips of spears as early as 1.2 million years ago, and it hasn't gone out of fashion. Today, some surgical scalpels have their tips sharpened to just 3 nanometers across, and the best material for this purpose is obsidian. Compared to the million-plus years we've been using glass, we only started making it very recently, around 5,600 years ago. Most common glass is composed mainly of oxygen and silicon, the two most abundant elements in Earth's crust. In nature, you find them in the form of quartz, crystalline silicon dioxide. Crystalline means that the atoms are arranged in a regular, repeating structure. and quartz is the primary constituent of sand. So if you take some sand, heat it up to about 1700 degrees Celsius until it melts, and then rapidly cool it, it forms glass. During the rapid cooling process, the atoms don't have enough time to return to their periodically arranged crystal structure. So instead, they are stuck where they are, like a liquid that's been flash frozen in place.
That is why glass is considered an amorphous solid. Amorphous just means disorganized, not in any regular arrangement.
But perhaps this is where the misconception about glass being a liquid comes from. It isn't a liquid. At room temperature, glass is solid because the atoms are fixed in place. They can't flow past each other like in a liquid. I even made a video about this 9 years ago. They are disordered, but they are solid. This amorphous structure is also what makes glass so brittle, because there's no way for the structure to relieve stress. When stress is applied to the glass, a small crack will form at a flaw on the surface. And as the glass cracks, the stress is applied to atoms with fewer neighbors, so the crack grows bigger, which eventually leads to the glass fracturing.
So next we'll move to what we call slapper demos. What we're using is sandpaper. This represents like an asphalt type surface.
Sure.
So if you were to get out of your car and you accidentally drop your phone in the parking lot, then what we're using is this fixture. It's bending it. So it's pre-stressing it. We have our rough surface to introduce the flaw. And on here we have an alternative glass, similar to some of the competitive stuff, different things on the market. And when you're ready, you can drop.
On 3, 2, 1. And some sounds. Okay.
Right? So bro, not what you want to see when you pick up your phone off the parking lot, right?
No. Hard break.
And then we have a Gorilla Glass and what we call the Mega Slap. Very exciting name, right? Now you can see me dramatically increase the height.
And I do it from here.
No, from the
very top.
From the very top.
Okay, so we're not just increasing the height, we're also starting from way up here.
Right.
All right, 3, 2, 1. No, we're good. That's pretty cool.
While the basic recipe for glass involves silicon dioxide, glass makers have been adding other ingredients to change its properties for thousands of years. Adding sodium carbonate, also known as soda, and calcium oxide, also known as lime, lowers the temperature at which it becomes liquid from 1700 degrees Celsius to around 1000 degrees Celsius. And that's why soda-lime glass accounts for around 90% of all glass manufactured today. Another recipe includes adding boron trioxide to the mixture, forming a borosilicate glass. Glass is usually quite sensitive to changes in temperature. If you throw boiling water on your car's windshield, it'll likely shatter due to the glass rapidly expanding. But borosilicate glass has a really low coefficient of thermal expansion. It doesn't grow or shrink very much, even with drastic temperature changes. So it's often used for laboratory glass, like beakers.
Let's go!
You want to grab a pair of these green glasses too?
Yeah.
Oh yeah.
I can't see anything.
And while this specific recipe for Gorilla Glass is secret, it is based on a combination of silicon, aluminum, magnesium, and sodium. And the recipe keeps changing. The scientists are constantly trying different formulations to find more durable and scratch-resistant glasses here.
This is so cool. Do you ever feel like a pizza chef? Right? What's like?
Good.
This facility is actually where that experimentation takes place. The earliest human-made glass was likely an accident. People had been working metal for thousands of years before they made glass. So it's thought that some sand made its way into metalworking furnaces, forming small glass beads. But soon, glassmaking became its own art form, to make decorations, ornaments, statues, tableware, and containers. Unlike clay, glass is impermeable to water, making it an ideal material for bowls and bottles. But then, glassmakers noticed that by adding other elements into the mix, they could change the color of the glass. By adding cobalt oxide, you would get a vivid blue. Adding cuprite makes red.
But all of the historical glasses we've been talking about have been opaque, which is not really what we think of as glass today. After glassmaking was invented, thousands of years passed before we invented transparent glass. That's because making it is actually pretty difficult.
The first step came around 100 AD, when glassmakers in Alexandria added manganese dioxide into the mixture, which led to a semi-opaque glass. It definitely wasn't transparent, but it did let some light through.
This is when glass began being used for windows. And glass windows were a huge deal. I mean, they provide a physical barrier that keeps the warm air in and the wind and critters out, while still allowing light to shine into your home.
But the first truly transparent glass was made many centuries later, around the Italian city of Venice. The art of glassmaking was thriving and bringing a lot of money into the city. There was just one problem. To make and manipulate glass, you need very hot furnaces. And at the time, Venice was a city built almost entirely out of wood. So yeah, glassmakers were bringing a lot of money into the city, but they also kept accidentally burning it down. So in 1291, the government of Venice had had enough, so they moved all the glassmakers to the island of Murano. The island became known as the Isle of Glass, celebrated for making the most beautiful and intricate glassware anywhere on Earth. This is also where the glassmaker Angelo Barovier invented clear glass. He took some seaweed rich in potassium oxide and manganese and burned it to create ash. Then he added this ash into his glass, and when it cooled, he found that the glass was transparent. Most materials are opaque because when photons hit them, the photons are absorbed. The photon excites an electron, pushing it up to a higher energy level. But this only happens when the photon's energy matches the energy of an allowed electron transition. And different materials have different energy levels. In transparent glass, the energy required to move an electron from a lower state to a higher state is higher than the amount of energy that a photon of visible light has. So the photon just passes right through. Now, while glass is transparent to visible light, it does interact with other parts of the electromagnetic spectrum. It absorbs much of the ultraviolet spectrum because UV photons have more energy, hence they can push the electron to the higher energy level and be absorbed. That makes it opaque to UV. This is also how colored glass is made. You add impurities into the glass, which affects the electron energy levels, which then changes the color of the glass.
If you look at a pane of glass side on, you might notice that it looks slightly green, which is because the most common glass used for windows, soda lime, has impurities of iron oxides, which give the glass a green tinge. The glass absorbs more of the other colors than it does green, so that's why we see it. I think the only way we'd truly appreciate how important transparent glass is would be if all of a sudden it disappeared. So your windows, glasses, screens, all gone. But there is another element in our daily lives that we take for granted, which is connectivity. I mean, we are always connected to the internet. And losing that connection, even for a few minutes, can be pretty uncomfortable, especially when you're traveling. Staying connected abroad requires either paying exorbitant roaming fees or a continuous hunt for public Wi-Fi. But luckily, you can avoid all of this with today's sponsor, Serlet. Serlet makes it incredibly easy to set up a cell plan with data in more than 150 countries. And it's way cheaper than roaming. I went to Germany for our recent Thermite video, and here's how easy it was to set up an eSIM with Serlet. After downloading the app to my phone, all I had to do was click on the country, select a plan, and activate the eSIM. Then when I landed, I instantly connected to a local network with no hidden charges. That was it. You don't have to use any shady public Wi-Fi or worry about scammers selling fake SIM cards in front of the airport. Download Serlet once and you'll always be connected. And if you find out that your phone isn't eSIM compatible, you'll get a full refund. To try Serlet, you can scan this QR code or click the link in the description. Make sure to use code Veritasium at checkout to get a special 15% off your first purchase. So I want to thank Serlet for sponsoring this part of the video, and now back to transparent glass.
Truly transparent glass was a massive deal for 3 reasons. Sometime in the early 1300s in northern Italy, this clear glass was ground, shaped, and polished into small discs that were thicker in the center than at the edges. Due to their resemblance to lentil beans, they became known as lenses. Glasses to correct farsightedness didn't seem all that important at the time because literacy rates were so low, they were almost exclusively used by monks. But after the invention of the printing press circa 1440, glasses became a vital tool. The printing press led to a precipitous drop in the cost of producing books, which led to a rapid increase in literacy rates. Now a large number of people became aware that they were farsighted. Thankfully, there was a technology available to solve the problem. 150 years later, a father and son, Hans and Zacharias Johnston, put 2 lenses in line with each other, rather than side by side. And this was likely the world's first microscope. It made objects appear about 20 times their original size. In the 1660s, Antony van Leeuwenhoek made significant improvements on the microscope by grinding the lenses himself. He could magnify things 200 times, allowing him to see human cells. A few years later, Robert Hooke published Micrographia, a book full of beautiful sketches of the microscopic world. And all of this was possible because of transparent glass. And in 1608, Hans Lippershey, an eyeglass maker, applied for a patent for a spyglass. His idea was for it to be used in warfare, to spy on your enemy on the battlefield. But the next year, Galileo Galilei heard about his idea and realized that he could point this device toward the sky to study the stars and planets. Galileo's telescope magnified objects in the night sky by about 30 times. In 1610, he was able to see the craters of the moon in detail, the phases of Venus, and 4 of Jupiter's largest moons. These observations were the final nail in the coffin for the geocentric model of the universe. He saw moons that were clearly revolving around Jupiter and not the Earth. And how else could you explain the phases of Venus other than to say that the planet must go around the sun? None of this would have been discovered without the invention of transparent glass. 4 centuries later, we can now make glass that is orders of magnitude more transparent than water. Glass that is so transparent that if you were able to make a column as deep as the Mariana Trench, you would be able to see all the way to the bottom. This is the glass inside optical fibers.
Oh, this is getting real. I'm stoked.
But the main thing we all need is durable glass. So how do you take a substance that is typically delicate and brittle and improve its scratch resistance and drop resistance? First, you start with an aluminosilicate base, and then, after the glass is made, you submerge it in a potassium salt solution at 420 degrees Celsius.
Yeah, it really does look like water.
Doesn't it?
Yeah. And don't know if I want to drink it.
Potassium and sodium are chemically very similar. I mean, they both have 1 electron in their outer shell. So during this process, some of the sodium atoms are replaced by potassium atoms in the glass. Now, potassium atoms are physically larger than sodium atoms, but the glass is already set. It's rigid, so it doesn't increase in size. So now there's the larger potassium atoms all squeezed together, taking up the same amount of space as before. This increases the compressive strength in the surface of the glass, which makes it more durable.
Can you see any visual difference in size between them?
Honestly, no. I have 2 pieces of glass. One of them has gone through the ion exchange process. The other one hasn't. I don't know which one is which. And we're going to figure that out really soon. You ready? 3, 2, 1. Okay. That's really cool. Can I get it harder?
Yeah.
That was a thunk. My mind is genuinely blown. That's really cool.
That's all just like ion exchange, right? That's all just... There's no other difference, right? You just put it in a bunch of salt.
Yep. For a few hours
For a few hours.
voila.
Yep.
I'm trying to think of a good analogy for this. You know, I can imagine if there were just a whole bunch of people sort of standing around casually and you try to run through them, you'd probably be able to bounce through a few of them, break through the crowd. But what if instead all of those people were squeezed together, shoulder to shoulder? You know, like people trying to get into a subway or something. If you try to run through them, all of those forces are just gonna add up and prevent you from getting in or from making a dent, making a crack, anything like that.
But the scientists at Corning are constantly trying to refine the process to make the glass even more durable. There is a whole team at the facility that is dedicated to testing and measuring different glass prototypes.
All right, we're displacing him by 1.5 millimeters.
Yep.
2 millimeters. Whoop.
And they really put the glass through its paces, conducting bending tests, scratching tests, and dropping heavy steel balls onto the glass.
3, 2, 1.
They also have replica phones with different glasses for the screen, and they drop them from ever-increasing heights.
But we can go up a little bit, and maybe
Right.
we can imagine that I'm taking a selfie.
All of this is to make the next version of Gorilla Glass even more durable than it already is.
Like, are we doing this?
If you want to.
Hell yeah.
1.7 meters.
Yeah, that's roughly selfie height. 3, 2, 1.
Amazing.
Go down and pick that up.
Still good.
Survived.
Dude, that's pretty wild.
You know, I think it's rather ironic that we are making this video right now while my phone looks like this. I don't know, can you see those? Yeah. So, it's still glass. It still cracks. It is not perfect yet. But it is constantly improving because scientists are working on ways to make this material more and more durable. And we have come such a long way. I am just appreciative that I can have this material. And it is amazing, even if it does still crack sometimes with people who just refuse to get a case for their phone.